Okay, so I'm going to talk to you today about the diurnal cycle of precipitation from observations, models, and reanalyses. For anyone wondering what the diurnal cycle is, it's just simply the fluctuations of precipitation throughout the day that I'm looking at. So a bit of an overview on my talk. So I'm going to introduce you to precipitation to begin with, why it's important to study precipitation and why you choose to look at the diurnal cycle in particular. I'll then introduce you to the observations that I use and the models and reanalyses as well. I'll then go through my methodology for determining the diurnal cycle from each of these products. I'll show you the global results, so the comparison between the diurnal cycle for each, and then I'll finally conclude. Okay, so to begin with, so precipitation, why is it important? So it's majorly important because it's a critical component of the water cycle of the Earth, but not just the water cycle, it also intertwines the water cycle with the energy budget as well. So it links to solar radiation incoming to the Earth, infrared radiation going outward as well. Another reason why it's important is because it's expected to increase with global warming. It also has many socio-economic impacts. So the amount of precipitation affects things like farming and agriculture. In severe cases where there's heavy precipitation events, you can get flooding, which can have a lot of impact. And also in the other case of severe events where there's no precipitation at all, that can affect things like water availability. So one of the key things that kind of motivates this study is where in terms of climate models, they struggle to simulate precipitation accurately. So when they do simulate precipitation, it occurs too often compared to observations, it's too light, and it occurs too early in the day on average. Okay, so in terms of observations, I use the Global Precipitation Measurement Mission, which is operated by NASA and the Japanese Space Agency. Here in this diagram, I show you the core observatory, so the main satellite of the GPM mission. This launched in February 2014. It has 2 instruments on board for measuring precipitation. So it has a radar, which measures at 2 frequencies. And the bonus of the radar is that, so you can see in this diagram here, the radar covers this swath of 245 kilometers. The radar has ranging capabilities, so it's able to measure precipitation at different heights throughout the atmosphere and below the clouds. So it can tell us about the evolution of the precipitation on the way down to the ground. And then there's also a microwave imager on board, which doesn't have the ranging capabilities, so it can't measure all the way down to the ground. But what it can do is it can measure over the entire column. So it gives you information on the precipitation within the column. Okay, and that core observatory by itself doesn't provide global precipitation measurements that frequently, but as part of a constellation of international satellites, each with their own microwave radiometer on board, which measures the column of precipitation as a whole. You're able, when they're each in their own orbit, you're able to get global measurements quite quickly then. So they combine together to measure 90% of the globe within 3 hours. So short kind of time latency to get information on precipitation around the globe. And this constellation of radiometers underpins NASA's 20-year global precipitation record, which is called iMerge. So the idea behind iMerge is that it combines these measurements from the radiometers. It uses other things called infrared sensors as well, which are capable to measure the clouds and tell you about the movement of the clouds and potentially the precipitation distribution underneath, and also ground-based gauges on the ground. So there's a lot of measurements going into that record. So as well, for the analyses, I use models from the coupled model into comparison project. This is simply just a vast array of different models, international models from around the world. In this work, I focus on 2 different models. So one from France called CNRM, and one from the US called NCAR. And these models are models of the whole atmosphere and the ocean. The ocean is constrained by observations of sea ice and sea surface temperature. And the atmosphere then is simulated based on those constraints. And I also use what's called reanalyses as well. So the idea behind this is a mixture of observations and models together. And the idea being that essentially the model will run, but then what the reanalyses will do is it will optimize the model estimates by essentially making the model bit closer to the observations that they have of the entire atmosphere. But what they do is they take into account the uncertainty on the observations as well. So they don't just fit the model to the observations, they fit them closely, and they inform the model, but the observations are not always perfect. And they do this in 12-hour windows. So the methodology for my study is that I assessed the diurnal cycle of precipitation in the months June, July, August from observations, models, and reanalyses. The reason why I picked June, July, August is because this is the summertime in the Northern Hemisphere, and the diurnal cycle has previously been found to be at its strongest in the summertime and overland. So that's kind of the influencing factor. Also as well, you might notice that for each of the observations, models, and reanalyses products that I use 20 years of data from observations and reanalyses, but 30 years of data from models. And the periods don't always overlap. So the reason why the periods don't overlap is because of the data availability, but assessment has been done to check that the results don't differ regardless of the period used. And this is the case. It doesn't matter what exact period we use. What's more important is that we use lots of data to ensure that the sampling of the cycle is good. And on the right-hand side here in this panel, I show an example observation of the diurnal cycle for over Florida in the US. And the idea is that you can see that each cross on this line here is the observations at a different hour throughout the day. And all I simply do is across the 20 years of data for the observations, I take the mean value at each hour of the day. And then what I do is I look at certain parameters of the diurnal cycle to assess it. So the parameters that I'm looking for in the first case are the mean of the diurnal cycle, which is just this pink dashed line here. So you can see the mean in this case is about 7.24 millimeters per day. It's quite high. Also, as well, I look for the amplitude of the cycle. So I'm looking at fluctuations of daily precipitation relative to the mean, which all I'm doing here is I take the maximum, subtract the minimum, which gives me an estimate of the amplitude, but I also take it relative to the mean as well, because there can be places where there's low precipitation and higher precipitation, and we're looking more at the relative fluctuations compared to the average. And then also as well, I look for the timer maximum. So the timer maximum in this case is represented by the red line, and that occurs at about 4 o'clock in the afternoon over Florida. So in terms of the novelty of this study, it's the first multi-decadal analyses of the diurnal cycle. So this has not been previously done across the entire globe before. And also it's the first study that evaluates model and reanalyses performance at the hourly timescale. So previously we only had observations that could provide global measurements down to 3 hours. Now we have them down to less than 1 hour, but we perform our analyses at 1 hour. Okay, so here I show the global results. So I have 4 panels here. The top left shows the observations, so the NASA iMerge 20-year record. And then each of the other 3 panels is a comparison of a reanalyses and the observations, or a model and the observations. So in the top right, I showed the ERA 5 reanalyses minus the NASA observations. Bottom left, I showed the US model NCAR minus the observations. And bottom right, I showed the French model CNRM minus the observations. And what I do is I take what's called a relative difference. So essentially what that means is that I take the difference divided by what the mean value that iMerge gives in this left-hand panel here, and that gives us essentially an estimate of how important that difference is. So whether there's a lot of precipitation there or not, and what's the difference relative to the mean precipitation from the observations. So the key things to note here are in the left-hand panel. What you can see is from the iMerge observations that precipitation tends to occur, or it tends to be highest in the tropical regions. So this band here is called the intertropical convergence zone, and that's where most precipitation occurs on Earth. Either side of that intertropical convergence zone is where we have the most arid regions on Earth, so the least precipitation. And these occur kind of west of the continents, but also over North Africa as well. And then just comparing the other products in terms of mean precipitation, we can see that the ERA 5 reanalyses does a good job over land. So you can see that there's a lot of white patches over land, which is good. It means there's good agreement between the two. But the only region where it tends to not perform so well is over the Asian continent, which is where you can see there's a lot of overestimates. So the reanalyses predicts higher precipitation than is observed. Then looking at the two models, we can see that their performance is not so good compared to ERA 5 over the land. So you can see that the model minus the observation tends to give blue colours in a lot of regions. This means that the model simulates less precipitation than observed. And that's the case in both of the two models, but what we can see is they have issues over at the Asian continent as well. So we can see that this is a region where, again, the models, just like the reanalyses, are predicting more precipitation. Next thing I show now is what I call the normalized amplitude. So this is the amplitude divided by the mean that I was talking about a few slides ago. The key things to note here, the layout of the panels is the same. The top left, I show the observations, and the first thing that you'll notice is that the observations suggest that the diurnal variations are much stronger over land. So these purple colours than they are over ocean. So in terms of over land, the mean amplitude tends to be about 54% of the mean precipitation. And over the ocean, the median value tends to be about 28% of the mean precipitation, so much lower. And there also tends to be a drop-off in the amplitude of the precipitation over ocean as you go down to 30 degrees south and below. And part of the reason for this is because in the southern hemisphere, it's the winter time, and the diurnal cycle tends to weaken outside of the summer. So a comparison again to each of the products shows that each of the reanalyses and the models tend to underpredict the amplitude or the diurnal variations of the precipitation throughout the day. And this is consistent across all of them. The differences then occur over land between the three products. So we can see that over land, the ERA 5 analyses tend to give overestimates of the diurnal variations. These are slightly smaller from the France model, and then the US model just tends to underpredict pretty much everywhere across the globe. And a thing to note here is I have these hatching regions, which are regions where the precipitation is low. So we don't trust the diurnal cycle in these regions because there's not enough precipitation in the first place to assess the signal. So we cover over them because we don't want to explore them any further. And then the final slide here that I show is the timer maximum. So the time when the precipitation peaks throughout the day. Here you'll see that there's even more hatching now. So the idea is that the hatching is over those regions where the precipitation is weak already, but we cover over the regions where the amplitude is low as well. So you can see that I was talking about the southern oceans previously having low amplitude or low diurnal variations in precipitation. And you can see that in those regions, we see that the timer maximum is quite noisy, which means that the signal is not strong enough to determine a timer maximum. It's not something that we really want to look at. So what we do is we just cover over it and we try and divert the eye more towards the true signals where you can see these homogeneous patterns of the timer maximum. So the thing to note here in terms of the results is that there's quite some differences between the observations, the reanalyses and the models. The observations suggest that precipitation tends to maximize in the evening. So they suggest that it tends to maximize between 4 o'clock in the kind of early evening towards about 9 o'clock in the evening. And then over regions where we kind of have mountainous terrain, we have propagation of precipitation. So we have the time of maximum tends to vary in a certain direction, like over the US here, where we have the Rockies in this region, and propagating eastward, then we see that the time maximum becomes later, which means that the precipitation system is moving eastward. And in those regions, we tend to get later time of maximum from the precipitation. So they occur between 9 o'clock in the evening and 6 in the morning. As we look at the coastal regions, then we can see that the time of maximum tends to be more around kind of midday. And as we go over to the open oceans, it's more in the morning. So it tends to occur between midnight and coming towards 10 o'clock in the morning. Then when we compare that to the other products, what we see is that over land for the reanalyses, for one, the first thing you'll notice is that it struggles to capture some of these regions where there's the influences of mountains or orography on the time of maximum. So it doesn't do so well at distinguishing these like we see in the observations. Also, it estimates precipitation to occur in advance. So those times are slightly earlier, tending to occur between 10 in the morning and 4 in the afternoon. And it's a similar story with the models, with performance being even worse in the models, especially in the French one, where you can see that it's suggesting that overland, for one, we're not really seeing any of the orographic effect, but also we see that the precipitation tends to maximize before midday, which is completely off from the observations. In terms of performance over the ocean, the performance is not so bad, but again, it's still in advance of the observations, and this is quite a big problem. So just to summarize what I've shown, so referring to NASA's 20-year record of observations, what we see is that the diurnal cycle of the precipitation tends to be stronger over land than over ocean. What we see is that we need a amplitude of about 30% to be able to see clear patterns in the time of maximum and times of maximum that we can trust. And where we do have those strong amplitudes, what we see is that precipitation tends to maximize between evening and early morning over land, and mid-morning to midday over ocean. And then in comparison to the observations, both the reanalyses and the models tend to underestimate the diurnal variations in precipitation throughout the day, and they tend to simulate maximum precipitation over land too early. Okay, and that's the end of my talk. Thank you for listening.